So this time I'm going to talk about unsupervised and semi-supervised learning of structure. This is something that I've actually been very interested in recently. Junchan, who's not here today, but he's an expert on this and has been working on some of the stuff. So I'll be talking about some of his stuff in addition to some other things. But supervised, unsupervised, and semi-supervised, most models we've handled so far are supervised learning, where we have y, which is something that we want to predict, and we have x, and at training time we're given both. Sometimes we're interested in unsupervised learning. So unsupervised learning is we want to model the probability of y given x, but at training time we're given only x. So in other words, we're not given any examples of the things that we actually want to be labeling. So an example of this, I'll give a couple examples of this in a second. And then semi-supervised learning, you're given both, essentially. You're given you're given some data that has both x and y, but in some data you're given only x. So the reason why this is important is obviously for a lot of tasks we care about, it's hard to get the labels that we're interested in. So we would like to leverage unlabeled data to do this. Before talking about this, I'd like to talk about the difference between learning features versus learning structure or learning the actual things that we want to output. So we've actually already talked about lots of semi-supervised learning methods, but all of them have been under the paradigm of learning features. So for example, we could be learning word embeddings or sentence embeddings or contextualized word embeddings. So in this case, basically what we're doing is with an unsupervised learning objective, we are taking this sentence and turning it into a vector or a sequence of vectors or something like that. In contrast, if we want to learn a discrete structure, we want to learn outputs of some type, we basically take in an input, and then our output is something that we actually can look at and care about and modulate, use to modulate information flow, etc. So a typical example of this is taking in a sentence and learning a dependency tree without having any dependency trees annotated in the first place. So why would we want to do this? I think there's two main reasons. One reason is we may want to model information flow differently based on the structure. So we talked about things like tree LSTMs or RNNGs and found that in some cases that these methods are better and give us better accuracy than others. But I think maybe the more important thing is that these things can be more interpretable than the features that we would be able to extract. So if we get a tree, then we can actually look and see the structure that the system learned and used. So a very quick review on unsupervised feature learning, what we've talked about so far. We have an objective function and use the intermediate states of the network to learn this objective. So for example, we had the continuous bag of words model for word2vec. We had skipgram models. We had sentence level autoencoders, so things like just an autoencoder, or also things like BERT, which are denoising autoencoders. We also had things like skip thought vectors, which predict the surrounding things, and of course BERT uses this as well. We also had variational autoencoders, so variational autoencoders could learn features. So all of these, basically what they're doing is they're learning continuous vectors, where that continuous vector can represent the whole sentence, or it can represent a each individual word in the sentence. And how did we use to learn features? We could use them to solve the tasks directly, like analogy tasks in word embeddings or text classification tasks. And by proxy, we could do things like knowledge-based completion, etc. We can also use them to initialize downstream models. So we can either use the extracted features directly in the models that we train from scratch, or we can use the initialized encoder to solve downstream tasks, which we do with like BERT and fine tuning, for example. So the question is, what about discrete structure? So one example of discrete structure is we could take words and we could cluster them together into specific clusters that we expect to be semantically meaningful in some way. We could also cluster words in context. So we could do part-of-speech tagging or named entity recognition, which are basically tagging tasks that take words in context and reduce them to a small number of discrete classes. Or we could learn structure, like tree structure or something else like this. And I'm going to talk about all of these. Also, what is our objective that we want to optimize here? So basically, for most semi-supervised learning objectives, including the ones that I've been talking about so far, we have some generative model of the data X. And sometimes this can be factorized as probability of Y, where we have a prior over the type of unsupervised structure or features that we expect. And then we generate X given the structure that we have found. You could also factorize it as P of Y given X, and then P of X given Y. So this is essentially an autoencoder type objective. So both of these are potential methods for doing so. And this method can be made mathematically correct, essentially, by using variational autoencoders. So if you remember in variational autoencoders, we have a Q function, Q of Y given X, and we get this to match the prior that we have. So essentially, the first one is a true generative model of the data X. So if you find a good structure that optimizes the model of the data, then this will improve the overall probability of the model. The autoencoder is not actually a generative model. You can't use it to calculate the probability of sentences, for example. But if you turn the autoencoder into a variational autoencoder, then you can use the prior and the posterior in the inference model here to calculate the probability of the data X. So we can basically get the modeling advantages of using an autoencoder while still having a true generative model that can optimize the probability of the data. Okay. Are there any questions so far, or is this okay? Okay. So now I'll move on to actual tasks that we can solve. So the first one I'm going to talk about is clustering words in context. So basically what this is doing is taking words, considering the context in which they occur, and coming up with salient clusters that we hear about. So a very simple first attempt is what we can do is we can train word embeddings and perform k-means clustering or any sort of other clustering algorithm on these word embeddings. This is an interesting thing that you can do. It's actually implemented in Word2Vec. I don't know if people have realized this. Word2Vec itself has an option called classes, which you can just run the software and add the classes option, and it will give you classes out of it. So this is interesting and can get you some reasonable results. Like all the names are clustered together, all the colors are clustered together, etc. But in reality, there's lots of words that kind of belong in different classes. So, for example, run, not run. Run's not a good example. Read is a good example. So READ can be read and read. So it can be a present tense verb or past tense verb, or things could have word sense ambiguity. So, you know, the famous one is bank and bank, where bank is a financial institution or it's the bank of a river. So maybe the more interesting problem is clustering words in context. One way of doing this, which I already talked about before a little bit, is hidden Markov models. Or actually, I think people know hidden Markov models, but I don't know if I've actually explicitly talked about it before. But hidden Markov models are basically a factored generative model of the output given some hidden structure. And they consist of state transition probabilities and also word emission probabilities. So if we wanted to train this in a supervised fashion, it's actually really simple to train the model. So we have the transition probabilities here, where we have the beginning of sentence followed by an adjective followed by a noun followed by a noun. Actually, sorry, this is reversed. A left bracket followed, left parentheses followed by a noun, etc. And then we also have the emission probabilities, which is the output of natural given adjective, the output of language given noun, etc. So this is familiar to people. Have you done this in NLP class, like algorithms for NLP or something like this? In general, yeah. Okay, so training this, so how do you train this in a supervised setting when you have a labeled corpus? Any ideas? How do you train a bigram language model? Yeah. Yeah, you just take the counts. You take the counts and you divide. So to get the probability of a noun following an adjective, you count the number of times a noun followed an adjective and divide by the number of adjectives. Similarly, for the number of times that language was emitted from, the number of times natural was emitted from an adjective. Sorry, I'm finding all kinds of bugs in my thing here. These should be nouns. The number of times natural was emitted from an adjective is the sum of the counts of natural and adjective divided by the number of adjectives. So what's a problem with this? What's the problem with bigram models in general, where you're just counting and dividing? I think I heard someone say it. Yeah, sparsity, there we go. So if you've never seen natural appear as an adjective, then you're gonna have problems, right? So one way, there's a couple of ways to get around this. One way to get around this is to not have labeled data at all. And you, what you do essentially is you change the labeled states to unlabeled numbers. So instead of having like adjective, noun, noun, you just have 13, 17, 17, 6, where you assume that these classes correspond to something that you care about. And basically, maybe if you know there's about 50 part of speech tags in your language, you set this to be 50 classes, and you train it in an unsupervised fashion to maximize the likelihood of the data. And the way you can do this essentially is you run, you randomly initialize the like emission probabilities of all of the states, and then you run the forward-backward algorithm, for example, to calculate the probabilities here, and use something like the expectation maximization algorithm to calculate the sufficient statistics to calculate all of these probabilities over the whole corpus, and then you do a similar thing. You count and divide. So this is what people did, for a long time. This has been used for things like unsupervised part of speech tagging, and the way it works is we don't necessarily know what class corresponds to an adjective, what class corresponds to a noun. So basically what you do is you take this class 13 and you find out which human class corresponds the best with it after you finish training. So basically, like, you take the 13, you say, oh, 13 co-occurs with adjective the most, so I'm going to assign all 13s to be an adjective. I'm going to take 17, and 17 co-occurs with nouns the most, so I'm going to assign all 17s to be nouns. And with doing this, you can actually get pretty reasonable results. Another thing is because the classes depend not only on the words, but also the context they appear in, you can have things like read be both a present tense verb and a past tense verb. So it won't necessarily only belong to a single class, but it can belong to multiple classes. Okay, but this doesn't have any neural networks or even any vectors, or well, it has some vectors, but it doesn't have any like word vectors or anything in it. So the next natural thing that people came up with, like as soon as word2vec and stuff came out, was doing hidden Markov models that have emissions that are based on Gaussian distributions. And the way this works is instead of parameterizing each state with a categorical distribution, so instead of like counting up and saying, okay, 13 has co-occurred with natural n times, so we're going to count 13 natural and then divide by the number of occurrences of 13. What we do instead is each state has a Gaussian distribution over word embeddings. So basically the way this works is 13 has its own Gaussian distribution, 6 has its own Gaussian distribution. But the means and the variances of these distributions are different for each state that you have. So if you have all of your nouns, kind of in this part of the space, and all of your verbs in this part of the space, and all of your adjectives in this part of the space, you assume the word vectors are kind of the same. You can have state number 17 have a Gaussian that looks like that. State number 13 have a Gaussian that looks like that. And state number 8 or whatever have a Gaussian that looks like that. So this is offloading most of the learning onto essentially word embeddings. So these models actually aren't anything new for NLP. Like they weren't invented by NLP. These were for a long time used as the de facto standard for speech-based models. But the fact that we had word embeddings now allows us to run them on NLP tasks as well, where we assume that similarity in word embedding space has something to do with part-of-speech tags. So specifically, this was applied to part-of-speech tagging by training to admit word embeddings by Lin et al., and this gave pretty robust improvements over the old methods. Is this clear? Any questions here? Okay, so another simple approximation that you can make to this. So basically, another way you can do this, instead of training a hidden Markov model over word embeddings, you can instead get contextualized word embeddings. So you can. Interestingly, this was done in 1992, far before Elmo or whatever, where they simply trained an RNN according to a standard loss function, for example, a language model, and then they took the states and clustered the hidden states according to k-means, etc. So the reason why I mentioned this is because theoretically you could do exactly the same thing with Elmo or Bert or whatever. I haven't seen a lot of work that has done this yet, but it's something you could easily think of trying out as well. So up until now, I've been talking about really simple models that basically take in word embeddings. There have also been a few methods that try to make this a little bit more rich and expressive using neural networks. So one example of this is essentially they take the hidden Markov models, and instead of having the hidden Markov models, like the normal way you define a hidden Markov model is you have the transition probabilities, which are just kind of discrete transition probabilities between states. that you count and divide to get. And then the emission probabilities, which maybe are Gaussian probabilities that you predict here. But you can also calculate these transition and emission probabilities directly using neural networks. So the way this particular work by Tran et al. 2016 did it was they calculated the representation of each word in the vocabulary with a CNN. And then they do the dot product of this CNN with the tag representation and do a softmax to calculate the emission probability. And for the transition matrix, they calculate the transition matrix using LSTMs. This is a little bit strange because they basically run an LSTM over the output and then calculate the transition matrix based on the LSTM, which kind of breaks the Markov assumption and turns it into a not actually a generative model that you can use to calculate any probability. But it's what they did here, and it did seem to work for the specific task of unsupervised part-of-speech tagging. So just to illustrate here, basically they have the tag embeddings and the word embeddings, and they calculate according to this, and then they run an LSTM over the entire thing, calculate the transition matrix, and use this to calculate the probability of the sentence. Okay, so I wanted to introduce this because it was kind of a precursor to this idea of using more complicated functions to calculate what you want to get. But we, and specifically Junchen, one of the TAs here, have come up with a method that is kind of elegant and can also be used in other types of models as well, so I'd like to introduce it. It also has some fundamental methods that you can use for other tasks as well, so I think we should, I can talk about those as well. So one problem here is that, as I just wrote on the board, if all your nouns are clustered together, all your verbs are clustered together, all your adjectives are clustered together, then you can assume that you have a Gaussian that you just put over these word embeddings, and it should give you good results for this unsupervised part-of-speech tagging or whatever. But in reality, that's not the case. So if you do a Tisney dimension reduction of word embeddings, and then you color each word embedding by their part of speech, you can see that actually it's not that simple. There is some clustering. So for example, the proper nouns are around here. So as I said, names are around here. You might have adverbs kind of be around here in their own part of the space. But things like plural nouns and singular nouns are basically all mixed together. You get some proper nouns with past tense verbs. I don't know why that's the case, but there's lots of things mixed up here. So the model that we propose to do this is basically to take this embedding space that we get from whatever model we use and convert it into a latent embedding space that is better modeled by our for example, hidden Markov model with Gaussian emissions. And the way it works is this, basically. So our generative story is that we have a hidden Markov model that has latent states. That's what these Z things are here. From each of these states, using a Gaussian distribution, we emit an embedding. So this Z is like a Markov structure. It's like a hidden Markov model. And then from each state, we emit according to a regular Gaussian distribution that has a mean and a variance. But then in addition to this, these X down here are the embeddings that we actually observed. And we transform these with a function that transforms from this simple space to a much more complicated space. So the reason why this is good is because basically what this means now is if we go back, we could have a single state that emits all of these singular nouns using a very complicated function that kind of gives high probability to the singular noun parts, gives low probability to the plural noun parts. By starting out with this Gaussian and then transforming it through a neural network to get the more complicated distribution. Actually, maybe those two are not the best illustration, but maybe the yellow one over here is a better illustration. This is not Gaussian. This is clearly, at least in the space that we projected into, it's clearly not Gaussian. But you could easily learn a neural network that basically converted a Gaussian into something that's kind of elongated like this, that covered the space. So that's what that neural projection would be. Okay, so this is the model. The only problem is, how do we train this model? And how can we train this using a neural network? One way that we could think of doing this is essentially we could take this complicated distribution, we could train a neural network to convert it into something that's conducive to modeling with a Gaussian, and then train our Gaussian to maximize the likelihood over this converted distribution. The problem with this, however, is there's a really simple degenerate solution that can give you infinite likelihood, which is map everything to 0, and then train a Gaussian with a mean of 0 and 0 variance. So you have this like infinitely peaky Gaussian around 0 that assigns like all of your probability mass to all the points that were mapped to 0. So if you just train the simple thing where you take a neural network and convert everything to a good space, then this will break and basically won't learn anything. And the reason why this is not a good idea is because essentially if you train a model that can do this, you're losing the information about where the point was originally. So you lose the ability to generate the original points, which were the things that a regular generative model would have had to do. Is this okay? Can people kind of... So basically, like in a normal generative model, we would have to generate all of these points according to a Gaussian, or something like this. But if we trained a model that mapped these into an easy to model space directly, then basically we would lose the ability to reconstruct this original space that we had. So is that okay? Can people follow this? Okay. Well, I'll move on. Feel free to ask questions later as well. So this will not work. This is not a solution to our problem here. So what we would like to do instead is we'd like to use a method called normalizing flow. And this is a general method that allows you to kind of map between two probability distributions in a way that's still well-founded. And it's really useful if you kind of want to model, like take a simple probability distribution and convert it into a more complicated probability distribution that fits your data well. So the way it works, basically, is you add an additional condition on your neural projector. So you have a neural projector that can project from the original kind of underlying latent distribution into the distribution of the data that you actually saw. But the condition on this neural projector, on this function, is this function also has to be invertible. So it has to be a function that there's a one-to-one mapping between all points in this space to all points in this space and vice versa. This is something, there are classes of functions that you can come up with and do this. And the reason why this is good is we can now optimize a very similar function to the one that I talked about before. So basically we have a Gaussian hidden Markov model over the mapped space. But instead of having the Gaussian hidden Markov model over something that maps directly here, we do this over the inversion of our actual neural projection function. And you can show by doing a little bit of math that if you take this log probability and add the log of the determinant of the derivative of the of the Jacobian of this function, this allows you to optimize this in a principled way that actually is maximizing the likelihood of the points that you got in your data distribution. And intuitively, if f is not invertible, like for example, if we had this degenerate function that mapped all of the points onto this point, this log determinant of the Jacobian would essentially become negative infinity. So it would infinitely penalize your model for coming up with this kind of bad transformation. On the other hand, if this is the identity, so if you don't do any transformation whatsoever, or you do something like an orthogonal transformation that doesn't result in any information loss, this term will become 0. So it gives you a trade-off between having a really complicated function that makes it possible to optimize this value well, and making sure that the function is invertible so you can actually recover the original data. Okay, so are there any questions here? So I won't go through the detail of all the classes of the functions that you can use here, but it's actually a pretty broad class of functions that are invertible, and you can calculate this value easily. One example of them is where essentially you can split the variables into two pieces, and if none of the variables in one piece interact with each other, when you calculate the probability, when you calculate the new values of the variables in one piece, then you can essentially come up with classes of functions that allow you to do this. So if you go back and read papers on this topic, they propose a bunch of different ways you can do this, even for like recurrent neural network type models as well. So the interesting thing is, this gives us the ability to take our latent embedding space, which we think is good for modeling using Gaussians. And the result of learning this is the latent embedding space that our model was able to learn when you ran it with a hidden Markov model. And you can see that basically it neatly partitions the space, not perfectly, but pretty well, into things that actually correspond to part of speech tags. And we have results, I don't think I put them on the slides, where you also compare that with what you get when you're doing it for a different task like dependency parsing. And the space looks very different, and you can tell it's kind of tailoring the embedding space to be good at these unsupervised tasks. So are there any questions about this? So this general tool of normalizing flow is a very interesting tool. So if you're working with distributions over things or anything like that, I encourage you to take a look at it. Okay. So the next thing I want to talk about is basically, I say phrase structured, but maybe I should say tree structured. So a few classes ago, we talked about tree structured composition functions that you can use for things like parsing, and we argued that they were good for capturing kind of long tail phenomena, et cetera. But these require things like syntactic parsers, and syntactic parsers, we can't get them for a lot of languages, and we're not necessarily guaranteed that the particular structure that we have is ideal for the tasks. So for example, there are different ways of creating dependency structure. Some dependency structures are very highly syntactic. Some dependency structures are very highly semantic. And based on this, you choose different heads, even when humans annotate things. So it's not clear which one would be useful for particular tasks, and it varies from task to task. So the question becomes, can we actually learn these structures to do well on downstream tasks? And there's a couple ways of doing this. One way is soft tree structure, and basically this means you use some sort of differentiable gating function that induces a structure. Or hard tree structure. This is non-differentiable, but it allows for kind of more complicated methods to compose together things like tree LSTMs, for example. So a hard one looks a little bit like this, and a soft one might look a little bit like this, where basically the hard one says, okay, you are composing together 2, 3, and 1 to get 1, 3, where in this case you might be composing together 2, 3, and 1 with a probability of 0.8, or 1, 2, and 3 with a probability of 0.2. So I mentioned supervised learning, semi-supervised learning, unsupervised learning, but there's one other paradigm called weak supervision, which is also an important thing to know about. So weak supervision basically is, in supervised we're given x and y to model p of y given x, unsupervised we're given only x, but in weakly supervised, we're given x and v to model p of y given x, under the assumption that y and v are correlated in some way. So an example of this, I think we maybe talked about this last time for semantic parsing, is questions and answers. So we assume that if you get the answer correct, or in order to get the answer correct, you need to get some underlying structure correct. There's also lots of other things, like for example, you could use it for text classification, where you assume that if you have a nice tree-structured composition function and you get the structure correct, it will be easier to do text classification than if you do it otherwise. One important thing to note is that this is different from multitask or transfer learning because we aren't given any examples of y. So we're only given x and v, and based on this, we need to predict y, which is some sort of underlying structure. So this is in contrast to multitask learning, where you're given some examples of x and y and lots of examples of x and v, and you assume that the underlying representations become better. It's also different from supervised learning with latent variables. So supervised learning with latent variables, which you can essentially do by like coming up with some sort of latent variable to solve your that's in between your input and your output for your supervised task. In weak supervision, very often it's the case that we actually care about the intermediate representation, not the final output. For example, if we are doing question answering with an unsupervised tree structure somewhere in our model, I would call it weak supervision if we care about the tree structure as opposed to the actual questions that we're answering. Is this clear? Or? Okay. So an example of a soft tree structure actually goes back to the very early days of neural machine translation, or of the current iteration of neural machine translation anyway, by Cho et al. In 2014. So they had something called gated convolution, where basically the gated convolution could choose whether to use the left node, the right node, or a combination of both. So they had this gate that either just inherited the information from the right, or inherited the information from the left, or inherited the information from some combination of the two. And when they trained this model, it could get something essentially here, where they like you had Obama, and it went all the way up to the top. Like starting from here, you just kind of passed the information all the way up to the top without combining Obama with other things. And over here, I guess it used the information from this node, but didn't use the information from this node. So you can kind of see that it's sort of looks like a tree structure that you might care about, but there's no really hard constraint that it does give you a tree structure. So people also know about GRUs, right? So actually, this was a predecessor to GRUs. So the GRU paper came after that, after they realized that they could turn this into a recurrent neural network as well. This is kind of a more general form of GRUs that later turned into the simpler form that we use for recurrent networks. And this was trained specifically using a machine translation loss. And the only way they evaluated it was using was by looking at it, I guess. So another way you can learn tree structures is with reinforcement learning. So the way this works is you have some sort of intermediate tree structured representation. For example, for language modeling, I believe they used recurrent neural network grammars here is their formulation for language modeling. And basically, they predict the tree using a shift-reduce parser, where the sentence representation is composed in a tree-structured manner. And then reinforcement learning is used. You can use it with a supervised loss to calculate the parser. Or you can use it with a loss that improves the probability of calculating the output on the language modeling task or something like this. And the way this works is basically if you do like shift, shift, reduce, shift, shift, reduce, reduce, you get this sort of tree. And when you calculate compositional representations for these nodes, these two nodes will be combined together, these two nodes will be combined together, et cetera. So this is in contrast to the previous one in that we actually have a discrete structure. We have a single discrete structure that we do to use to perform the composition. And the good thing about this is essentially this allows us to use whatever arbitrary composition function we want. Like we could run a BILSTM over the children and calculate, for example, and calculate the next representation, for example. However, this actually has lots of problems. One of the big problems with it is if you're jointly training. So like let's say you have the probability, you have the agent, the reinforcement learning agent that calculates the probability of the tree given the input. And then you also have the agent or the parser. You also have the reward function, which is maybe the reward of calculating some output given the tree. And this could be like a decoder or something like this. The problem here is basically if your decoder is at the very beginning of training, your parser is not good. It can't find any meaningful structures, so it will very often kind of degenerate into these structures here. So basically, at the very beginning, you'll learn an agent that only predicts kind of like left branching structures like this, or more likely, you'll come up with an agent that predicts all shifts at the beginning, and then when it can't shift anymore, it will just reduce everything. So you'll learn a really simple strategy that doesn't work very well, but at least it's consistent. And because that strategy is consistent, your decoder will be able to do better on that strategy because it will be easier to learn than learning from an agent that does kind of random things that don't make very much sense. So it's very easy to fall into, in this training paradigm, it's very easy to fall into kind of like local optima, where you learn a really, really stupid, simple agent at the beginning, but then you can't recover from it because your decoder only knows how to respond to that agent, essentially. So this is a really big problem, and it makes it really hard to learn these things well. So another method that was a little bit more successful, but still I don't think super successful, was this learning with layer-wise reductions. And basically what they do is at each level, they have a softmax, essentially, that decides which two constituents to reduce into a single constituent. So the way they do this is by calculating the softmax over each pair of representations, and whichever one has the highest value essentially gets composed. And they can actually do this in a soft manner. Depending on the composition function you use, you can actually do this in a soft manner that's fully differentiable or close to fully differentiable. This gives you better results. Actually, I'm sorry, no, this is not fully differentiable. What they're doing is they're using the Gumbel straight-through trick that allows you to basically back propagate into these decisions, but pick a single one to do the composition over. The experiments that they have here show that this was faster to train and more effective than RL. And follow-up work found that compared the two found that this gives less trivial trees. It gives you, at least trees that learn at the very low level to do better composition than the other methods that you could come up with. Are there any questions about this so far? Okay. So one of the reasons why I like this problem is I think it's still a completely open problem. We do have methods that don't work quite as well and methods that work a little bit better. But actually, it's still really hard. And I think this is a really fundamental problem where if you have some downstream model that uses structure and an upstream model that tries to predict structure, how can you get the good structure that the downstream model can use while you're simultaneously training the model that uses it? And as I said, unfortunately, many models learn trivial structure like this. And we have an explanation for this. And actually, I'm sorry, I think I cited the wrong paper here, but they actually have some follow-up work where they create a data set that is super simple to solve if you get the structure correct, but it's extremely difficult to solve if you don't get the structure correct. And specifically, it's mathematical equations. So mathematical equations, or essentially, based on the order of operations and things like this, you can come up with a tree structure where it's like A plus B times C. And your tree structure is essentially multiply and then add. So if you do the addition first and then the multiplication second, then you get the answer wrong, right? It's as simple as that. So they created a synthetic data set that has equations of this form and tried to solve it with various methods. And LSTMs don't work. They don't generalize. The latent tree learning methods also don't work because they don't learn the correct structure. So I think it's interesting because you can see there are data sets that do where the structure is useful and we're just not being able to learn it. So it's a good challenge problem if you're interested in learning algorithms for this. Okay. So I talked about learning kind of phrase structures. I'll talk pretty briefly about learning dependencies. So a common model for doing this is the dependency model with valence. So actually, one important thing that I kind of forgot to mention explicitly is one reason why one reason why this problem is hard um, when you do it in kind of an unrestricted setting is if your decoder is really strong, your model doesn't necessarily need to get meaningful structure in order to get the answer correct. So, for example, if you just tried to train an LSTM language model that had like discrete states in the language model in some way, if you have this big vector, you have this big LSTM vector that has like 512 states here, 512 continuous variables here. And then you have another vector that has like a discrete like state or something like this. So these would be like 0.2, 0.5, 0.7, minus 0.1, or whatever. Basically, if you have a really strong LSTM language model, it's not going to need to use these discrete states to do a good job at the task, right? So based on that, it will have very little pressure to learn these well. So things like hidden Markov models essentially prevent this problem by making your generative model very weak. For example, they have a Markov assumption where you only look at the surrounding words, and based on the surrounding words, you need to get a class, and then you predict the word based only on the class. So essentially, if you create an underlying model that is very weak, it essentially makes the decoder not able to do well unless you predict good structure. And if you make the decoder not able to do well unless you predict good structure, then you put a lot more pressure on the agent to do a good job at learning that structure. So this is a pretty common thing to do in unsupervised learning, and there's also methods to do this for dependencies. And specifically, there is the dependency model with valence, which has been a super popular model for doing this. And it's basically a top-down dependency-based language model that generates the left and right sides, and then stops. And then for both of the the left and right side, calculate whether to continue generating words. And if yes, generate. So to give an example here, if we have the word saw, the way this works is we say on the word is saw, we condition on the word saw, we condition on the fact that we're generating left, and we can then we generate false. Sorry, this is whether we've already generated a word on the left side or not. So if the answer is continue, then we generate a word. So saw has a word to its left, so we generate I. Then based on this, now we have a next word, so our probability is saw. We're still going to the left, and we've already generated a word before. So now we generate stop, because there's no more words on the left of saw. Then we move to generating on the right. We generate continue because saw has one child on the right, has at least one child on the right. We generate the word girl, which is the child of saw. Then we continue again. We generate the word with, which is another child of saw, and then we do this. So like the details aren't so important other than the fact that this is essentially a hidden Markov, like a hidden Markov model over trees. It's a very simple model that has strong Markov assumptions that we're only conditioning on the parent, et cetera. So there have also been methods that try to do this with neural nets. And the simple idea is to parameterize the decision with neural nets instead of with count-based distributions. And like the DMV, train with the expectation maximization algorithm. So basically what they're doing is they're relying on the fact that you expect the neural network to be a better method of parameterizing this function than a regular kind of a regular count-based model. So your neural network takes in saw, it takes in left, it takes in false, and then it tries to predict the action. Then it takes in saw, it takes in left, it takes in false, and tries to predict I. So this is one way of doing things. And in our, or in Jinshan's work, we also tried the exact same method that he had, that he used for part of speech induction, but we used it for dependency parsing as well. So basically, the only difference is that instead of using a hidden Markov model up here, we have the DMV, the dependency model with valence up here, that generates Gaussian embeddings, or generates Gaussians over a latent embedding space. And then from this latent embedding space, we generate the actual embeddings. And it turns out this model works really well. We got excellent results doing this. So this kind of shows that the invertible flow is a good method for kind of learning generative models over these word embeddings here. Are there any questions about this? Okay. So another example, I think this is a kind of interesting, this is kind of an interesting general method as well as a specific example for dependency parsing. But this is work by Adi Kuncoro, who was here at the time. Given a phrase structure tree, we might want to know what child is the head word, or in other words, the most important word in the phrase. And the idea is to create a phrase composition function that uses attention and examine if the attention weights follow the heads, dependency heads as defined by linguists. So the composition function, basically the way it works is we give it a phrase and it needs to combine together all of the children into a single input. And in order to do this, it just does attention over all of the children. And then we look at the word that gets the maximum amount of attention and try to figure out whether this actually makes sense according to our intuition. And so, for example, we have Canadian Auto Workers Union president. In this case, maybe president would be the normal head, but for some reason it decided to focus on auto. In this case, it actually does get corporation, which I would say is the normal head. In this case, it got real estate assets. It got real and assets. So you can see in some cases, it follows what we would expect. In some cases, it doesn't. For Apple, Compaq, and IBM, I kind of like this one. Apple got the highest weight. IBM got the second highest weight, and Compaq got the lowest weight. This was from the Wall Street Journal in like the 1980s. And now Apple is doing very well. IBM's doing pretty well, and Compaq is out of business. So our attention model actually is somewhat prescient in addition to being able to parse well. But there's lots of other interesting examples. But what I wanted to say here is what we did in this paper on a more general level is we took something like a bi-LSTM, where the bi-LSTM is not very interpretable, it's not very easy to tell what it's doing, and we replaced it with attention, where you can just somewhat interpret the attention weights. And this is things you could do in other models as well. So like if there's some structure that you think would be important, you can essentially try to use attention to figure it out in some way. And there's actually another example that I didn't, let's see. I'll have to find the name of the paper. So here's another example of something like this called context-aware neural machine translation learns an AFRA resolution. And basically they train a model that does attention over previous sentences. And they can find that the So for example, here, where's the example? I haven't looked at this in a while. Yeah, okay. It in heart, yeah, there we go. So we have it. So this is the previous, this is it in the next sentence, and then this is heart in the previous sentence. And you can see that essentially just by training a neural MT model that has access to the previous sentence, you can kind of look at the attention weights and say, oh, we have a pronoun here. What is this pronoun attending to? It seems like it's attending to the word heart, so maybe it is referring to the word heart. So, and then they also find out how good is this compared to Stanford Core NLP, which is something that was explicitly trained to do this co-reference resolution. And the answer is basically they're pretty similar. They get more than half right, and of the ones they get wrong, they split them about half and half, about one being right and the other being wrong. So yeah, there's some interesting examples of how you can do things like this. I have one more in the other examples part. Are there any questions about the stuff here? Okay. So this is another example of how you can use attention that I thought was kind of clever. So this is work on very low resource languages. And the idea is that we can take a MT system and run it over kind of character-based input. And the attention that the MT system uses can be used to essentially segment words into meaningful units. So for example, when they generate the first word, it attends to these two characters. When they generate the next word, it attends to these two characters, et cetera. And you can kind of see that it forms consistent chunks. And then the red boxes are the actual correct word boundaries in this language. And you can see that the attention kind of corresponds to the boundaries in the words. So you could think of something where, I don't know, if you had even just in English, if you had a big long document that you wanted to segment into particular parts, you could look at how it attends to each of the parts as it's solving a task about each of the parts. And use that to segment the document as well. Another way that people have tried to learn segmenting things is segmenting of speech and text. And the idea being that, let's say you have a big speech stream in some language that you don't know and you want to find words in it. So this is the goal of basically finding boundaries of words in speech or text, kind of like babies do when they're very young, et cetera. And the idea is that consistent segmentation should result in easier to reconstruct segments. So the way it works is basically you have an utterance encoder that learns how to segment the utterance into contiguous segments. And then it learns how to reconstruct the segments. It learns how to reconstruct the segments based on just the representation here. So the idea being that, let's say you have a utterance, you have an encoder that learns consistent words. It should learn words like hello. To have a very simple representation, and then every time you have hello, you can just read off hello from here. But if you make segmentations that don't make very much sense, basically you'll have more randomness in the things that you need to output. So it will be harder to compress this into a small representation and reconstruct things well. Then a final thing, this is also work that we did a couple of years ago. I think this is kind of interesting because it takes a different approach of learning about a whole language as opposed to learning, about individual sentences. And the idea being, can we learn typology, which is like, what is, some examples of typology are, what is the canonical word order of the language? So like English and French are subject verb object languages. Hindi and Japanese are subject object verb languages. English and Japanese put the adjective before the noun, and French and Spanish put the adjective after the noun, etc. So these are features, and they're features of the whole language, not any individual sentence in the language. But what we did basically was we trained a neural MT system on 1,000 languages, and we have a embedding for each of the languages that we feed into the neural MT system. And the hope is that by, when the neural MT system learns these embeddings well, it will be able to do better on the MT task, which we can then use to train like a typology classifier that predicts these discrete features of the language. So this is less structure. This is more like finding discrete features of the language from continuous features that are learned from a typology classifier. But I still think this might be a kind of interesting example. And specifically, we use two different types of things. One, we had a language embedding that we just fed into the input sentence all the time. The other thing was that we averaged the states of the encoder for that particular language. And both of these seem to help to some extent. Okay. So this is all I have for today. Are there any questions or things that people would like to ask? I think a lot of the methods here are actually rather technically sophisticated. It's pretty hard to do broad coverage and do all of them here, but hopefully some people find these interesting and maybe can go and read the papers more deeply, et cetera. Any quick questions or? No? Okay, I will finish up. Thank you.